The fundamental baseline rule for most of chemistry is that atoms reach a state of stability by sharing pairs of electrons. This creates a two-center, two-electron bond, the standard unit of molecular architecture. Methane is the model example. Carbon uses 8 shared electrons to form 4 identical connections with hydrogen, perfectly satisfying the requirements for a stable octet. However, the P block of the periodic table contains stable molecules that exist despite having an insufficient number of electrons to satisfy this unit. Applying these standard rules to diborane leaves the structure completely disconnected, with missing links in the center of the molecule. On paper, diborane simply lacks the necessary valence electrons required to hold its atoms together in a standard ethane-like configuration. By auditing the hydrides of group 13 and the structures of groups 14 and 15, we can see how elements adapt to these mathematical deficits. This electron deficit forces the atoms to adopt unusual geometric forms, sharing a single pair of electrons across multiple nuclei to maintain structural integrity. To understand how boron bridges this gap, we have to audit its available electrons. A boron atom has 3 valence electrons. To prepare for bonding, it reorganizes these into 4 sp3 hybridized orbitals. If we bring in the components of a diboron molecule, 2 borons and 6 hydrogens, the math becomes problematic. 2 boron atoms provide 6 valence electrons, and 6 hydrogens provide 6 more. That is a total of 12 available electrons. To build a structure similar to ethane, the atoms would need to form 7 separate bonds. 7 bonds require 14 electrons, meaning this configuration is 2 electrons short of what the standard model requires. Under classical rules, diborane should not be able to hold its shape. Because this gas is stable and industrially useful, it serves as evidence that atoms can connect in ways the standard Lewis model does not predict. Diborane solves this deficiency by spreading a single electron pair across 3 different atoms. Boron first uses 4 electrons to secure the ends of the molecule, forming standard 2-center bonds with 4 terminal hydrogens. This leaves 2 leftover orbitals on each boron atom, one containing a single electron and the other completely empty. The 2 remaining hydrogens move into a plane perpendicular to the rest of the molecule. A single electron pair now occupies an orbital that overlaps with both borons and the central hydrogen. One pair is shared among all 3 nuclei. This is a 3-center, 2-electron bond. These central hydrogen bridges act as locks, preventing the boron atoms from rotating and creating a rigid molecular frame. When atoms lack enough electrons for simple pairs, they use these multi-atom bridges to achieve stability through shared geometric space. In group 14, we can see how shifting this orbital geometry changes the tangible properties of solid matter. Carbon demonstrates this phenomenon perfectly through diamond. Its extreme physical hardness and total electrical resistance are incredibly well known. These properties stem from sp3 hybridization, where every carbon electron is locked into a rigid 4-way lattice with bond lengths of exactly 1.54 angstroms. If we remove the vertical connections and flatten the structure into horizontal sheets, the material changes completely. This is graphite, which utilizes sp2 hybridization. Crystallographic data shows carbon bonds within layers are strong, but layers are separated by a 335 picometer gap. Because this gap is large, the sheets slide over one another, making graphite soft enough to act as a lubricant. Electrons in the remaining unhybridized orbitals are free to move across the sheets, allowing graphite to conduct electricity where diamond cannot. The difference between the hardest natural material and a soft pencil lead is a direct consequence of internal orbital geometry. In group 15, internal pressure from electron pairs can force even more anomalies. Phosphorus pentachloride in its gas phase provides a clear example of geometric distortion. It uses sp3d hybridization to create a trigonal bipyramidal shape with 3 equatorial chlorine atoms and 2 axial atoms. The axial electron pairs experience more intense repulsion from their neighbors than the equatorial pairs do. To minimize this pressure, the axial bonds are forced to become physically longer and weaker than the bonds around the center. These molecules are not static diagrams. They are objects that warp their own dimensions to balance internal electrical forces. These p-block elements show us that molecular shape is a product of necessity. Elements with too few electrons will invent multi-center bridges to stay connected. Variations in hybridization will change how the same element behaves as a bulk solid, and internal repulsion will stretch bond lengths to maintain stability. Chemical bonds are spatial balances of electrical charge and orbital overlap, rather than static lines on a page. Whether an element forms a rigid bridge or a sliding sheet depends on how it manages its electrons within the available space. Molecular geometry is the physical resolution of space, charge, and the availability of electrons.